చిన్నగా బీపీని కంట్రోల్ పెట్టుకుంటాం. అంతకు మించి వేరే మాత్రం లేదు.
బీపీ మిషన్ బాగుంది చేసుకొని రోజుకి ఒకసారి చూపించుకుంటా ఉంటే రెండు రకాలు. హై బీపీ ఎక్కువగా ఉన్నప్పుడు ఈ బిళ్ళ వేస్తామని ఇంకొక బిళ్ళ ఇచ్చారు. ఎంతైనా అమ్మమ్మ తాతయ్య 60 ఏళ్ళకు పోయి ఉంటారు. 62 అమ్మమ్మ 62 తాతయ్య 60.
అలా నగోడుదిలేమా ఎందుకు
నాన్న ఉండకూడదు సార్.
అన్న అదృష్టవంతులు అనుకుంటే ఏం లేదా ఇంకా అది ఎందుకు పూర్ణాయుష్యం అనుభవించడం ముఖ్యంగానే.
మనసులో ఎన్ని రోజులు వచ్చింది. ఫిజియోథెరపీలో వస్తువులు మనం బయట కొనుక్కొని మనం తయారు చేస్తాం. ఏముందా కట్టికి దయచుకుంటే సరే తాడు
దీన్ని పెట్టి తాడు అటు ఇటు లాడు అట్లా అట్లా అట్లా.
అదే మరి దానికి ఆయన రోజుకి 150 200.
అలా కాదు ఇంకా వేరే అయ్యో పెడతాడు హీట్.
అదేదో మిషన్
హీట్ పెడుతుంది హీట్ పెడతారు కదా.
సుబ్బారామయ్య అదే కొనుక్కొచ్చి పెట్టారు. అది రోజు ఆవిడ 6 గంటల సేపు. ఆన్లైన్లో మనకు పంపిస్తారు. ఆన్లైన్లో తెప్పించుకొని ఇంకోటి ఏదో ఉందంటారా అది అంట బీపీ కంట్రోల్గా ఉంటుందంట. ఏదో ఆయిల్ అంట. అది కూడా ఆన్లైన్లోనే తెప్పించుకొని అది ఇది కలిపి రోజు ఎంత ఇంతవరకు పోసుకుంటాను. ఎవరో 110 మిలాయించి జరగట్లేదు. శ్రీనివాస్ ఎంత ఆరోగ్యంగా ఉందోనంట. ఆడికి 110 కన్నా మీరు జరగట్లేదండి. మీరు కూడా ఈ తెప్పించుకొని తాగుండక గతాలు మీరు ఎవరో కంట్రోల్గా ఉంటుంది, బీపీ కంట్రోల్గా ఉంటుందా అని చూస్తున్నారు. ఫోన్ చేసి కనుక్కుంటూ చెప్తాడు ఏం వాడితే మంచిది. చిన్నీళ్ళపాయలు ఒక 100 గ్రాములు అల్లం 100, చిన్నీళ్ళపాయలు 100, అల్లం 100. చిన్నీళ్ళపాయలు పొట్టు తీసాము, పై పొట్టు తీసేసి లోపల పప్పు ఆ పప్పులాగా తీసే అల్లం కూడా పొట్టు తీసేసి మొత్తం కలిపి మిర్చి వేసి జ్యూస్ వడపట్టి ఇప్పి బాధేసేసి అది ఒక సీసాల్లో రెండు విడివిడిగా సీసాల్లో వేసుకొని ఫ్రిడ్జ్లో పెట్టుకొని అంతేమో అల్లపు రసం, అంతేమో చిన్నీళ్ళపాయలు, ఒక నిమ్మకాయ చెక్క, ఈ విసిట్ ఏమన్నా ఒక మూత. ఇంకోటి చెప్పాడు.
అవును సరే కానీ మోయ్ మీ మొన్న కాగితాలు ఇచ్చాను తీసుకో. అయితే బయటిది 2 కాపీలు కావాలిగా, ఆధార్ పాన్ కార్డులు తీసుకురా. బయట లోపల పెడితే అట్లా తీసుకెళ్ళాలిగా. అవి తీసుకెళ్ళాలి. అక్కడ ఫోటోలు పెట్టాను, అవి కూడా తీసుకో అద్దం ముందు.
So I think I have unmuted myself. Video is recording. Okay, so uh, we'll start today's discussion. So yeah, we are discussing about the convection heat transfer today, along in addition to what we have discussed earlier. So this is for week 5 of the course, and week 5. So the syllabus for week 5 was, I think it started from the what do you say, order of magnitude analysis. Then there was discussion about different transport coefficients, and then uh, you know discussion on momentum, thermal, and concentration boundary layer. And then Reynolds and Chilton-Colbert analogy was discussed. Reynolds analogy is basically for Prandtl number 1, and if Prandtl number is other than 1, this Chilton-Colbert, Reynolds Chilton-Colbert analogies are there. And then forced convection introduction was there. I think forced convection uh, will be discussed in the next week also in detail, so we'll not go there right now. So we'll start. So basically, there are certain things that first of all, this. So sometimes it is also called as scaling analysis. So essentially, this is a technique where you neglect some of the terms in your governing equations and simplify them, and that makes them easy to solve, easy to compute. Sometimes what is observed is in your governing equation, uh, depending on your boundary and initial conditions, your flow regime, your fluid properties, there will be certain terms in your governing equations which will not be relevant. But if you don't do scaling, and if you don't understand which term is important, which is the driving term in your governing equation, then you are solving the whole governing equation, and sometimes it will be computationally expensive. Sometimes it may not converge also. You will not get closed form solution also. So therefore, this technique is used, order of magnitude analysis. It is used in multiple places, not only in heat transfer or convection heat transfer. Uh, it is used in almost, it can be used almost anywhere. For example, porous media flow also, one can use it. In porous media there is heat transfer as well as flow of the fluid through the porous medium. So there are two scales there, and which, depending on which scale or which phenomena dominates the performance of the porous medium, then you need to solve different sort of governing equations to understand the performance of the process. So the point is, this scaling analysis is very widely used method, and for our course it is it's basically related to the uh, what you say, it is related to the flat plate boundary layer, like that, uh, both the hydrodynamic boundary layer or momentum boundary layer, or and thermal boundary layer. Concentration boundary layer also you can use it, no issues. But as professor discussed in the class, the energy equation and the concentration or the mass conservation equation, not mass conservation, you should say concentration, or mass balance also you can say, species conservation also sometimes people call it. But this energy and mass balance equations or concentration equations, uh, they typically have similar form. So, and in case of momentum equation, there is one additional term which is the pressure gradient. And since we are discussing the forced convection case, typically that pressure gradient in the flow direction is assumed to be constant. So therefore, these three equations essentially boil down to a similar sort of form, and therefore we can assume similar sort of solution also for them. and that's where this Reynolds Goldberg analogy, etc., comes into picture. But regarding the order of magnitude analysis, some things that I wanted to discuss. Uh, okay, so yeah, so one thing is it's very, I mean, order of magnitude or scaling thing. You can use it to derive very good uh, correlations, not the exact ones, but somewhat intuitive ones. For example, uh, how should I say this? Uh, yeah. So, for example, see, you have x momentum equation. So, for a flow over a flat plate, you have x momentum equation, which is given as u del u by del x. This is the simplified one. V del u by del y equal to minus 1 by rho del p by del x plus kinematic viscosity into del square u by del y square. So if you do scaling here, and I want you to focus on, see, in scaling, all the terms will be having same scales. So first term, if you consider u infinity as your free stream velocity into u infinity by L, which is your length, and then you will have last term again scaled as kinematic viscosity remains as it is, u infinity remains as it is, and there is y square. So that is your kinematic or hydrodynamic momentum boundary layer, whatever you want to call it, and this is your momentum boundary layer thickness delta. So you know that all the terms should have same scales, similar scales. Otherwise, if any term has not, then you neglect that term. So in this case, we have already neglected terms which are having less importance or less significance. So all these terms represent significant terms in your fluid flow. So if you compare these two terms, so you have u infinity square by L on one side, you have gamma u infinity by delta square on the other side. So that gives you delta square by L proportional to gamma by u infinity. Correct. Now what you do, you multiply or divide by L on the both sides. So this becomes L square, this becomes u infinity into L. And as we all know, this Reynolds number at L is nothing but u infinity L by kinematic viscosity. So that is what we are getting here. So therefore, delta by L scales as Reynolds number power minus 1 by 2. So you get the scale from here. And if you check the governing equations, or maybe in the next class we'll have some exact correlations. So there is only one constant. So basically, if you see exactly, if you solve the or do experiments and get the correlation, so we will have some constant and you will get the same thing as what we have got here. So scaling gives you this flexibility, so that you need not have to solve all the equations, but you'll have the idea that okay, boundary layer thickness will vary with respect to Reynolds number in this fashion. So that's what I wanted to say. And then uh, sir has discussed in the class that uh, the del p by del y is almost zero. So there is no pressure change in the boundary condition, and this you get from y momentum equation. So these are I am highlighting these points because these are very important points, and in some competitive exams they are directly given as MCQs. So you should know, and therefore you know yeah, one more thing is asked basically, that okay, del p by del y is 0, then what about del p by del x? Is it a constant? That is also a famous question. So we understood that y direction pressure gradient is 0, but in x direction there is a pressure gradient, and will it be changing or constant or whatever it is. So for that you can use you know see, it goes like this. So if this is your flat plate and if this is your boundary layer, and let's say this is your flow u infinity, t infinity, and this is your x direction, this is your y direction. So this is the typical setting that you have, and this is your delta, correct? uh, for right now only assume that this is a momentum boundary layer, there is only that case. So in that case what you do is you consider this point number 1. So at point 1 flow is inviscid. What do I mean by inviscid? That velocity is constant throughout. So u infinity is constant there at point 1. So, and you can apply Bernoulli's equation there, since it is inviscid and is rotational also, it's unidirectional flow. You have this as your Bernoulli's equation, right? It is denoted in terms of you know, per unit density, like that. And now you differentiate it. So what you get is d infinity by dx, 1 by rho remains as it is, plus 1 by 2 u infinity du infinity by dx, and the constant integration will be 0. So this 2 gets cancelled, and therefore what you are end up with is you'll get minus 1 by rho infinity dp infinity by dx equal to u infinity du infinity by dx, and this will be 0 because since u infinity is constant, your differentiation of any constant is 0. So that means this pressure at point 1 pressure gradient is 0, but we know that okay, for sake of simplicity I can move this point to somewhere here. So this is my point number 1. So and then if you draw a vertical line and if you consider point 2 here inside the domain, inside the boundary layer, so since del p pi by del y is 0 that we got from the y momentum equation, dp by dx at point 1 will be equal to dp by dx at point 2, right? Because there is no change in pressure in y direction. So whatever change is there, that will be in x direction. And since at point 1 it is dp infinity by dx, and at point it is, let's say, dp by dx, it is 0. So basically what I mean is this pressure gradient in x direction is 0, but that is only valid for flat plate. Am I correct? Yeah. So you should remember that valid only for flat plate. What happens if it's a curved plate or curvature or something? Then you cannot use Bernoulli's equation because there the flow is rotational and Bernoulli's equation is not valid, as well as there will be vortices, etc. So for flat plate, this is an important thing that you should remember. First is your y momentum, pressure gradient in y direction is almost 0, negligible. and in x direction also the pressure gradient remains constant. I mean, pressure is constant, pressure gradient goes to 0 for flat plate. Okay, so what I mean is this term itself will go away because dp by dx is 0. So you only have this term and the last term. And that's where, by further doing these things, yeah, and let me see. We have to discuss this Reynolds-Colburn also, right? So, hmm. Okay. I hope the point is clear. See, again, this is only valid for flat plate. Okay. So if it is pipe flow or something, this is not valid. This is valid only for a flat plate. Right now we are discussing flat plate only, so that is okay. But you should remember this because in pipe flow you cannot assume this, otherwise it's wrong. Anyway, so what happens? Yeah. So this Reynolds-Colburn analogy, there is one way also to get back to it. I'll just do it. So see, if Prandtl number is 1, so that means your kinematic viscosity is equal to your what do you call, kinematic viscosity is equal to your alpha thermal diffusivity, or yeah, k by rho Cp, whatever it is, and then your uh, scaled x momentum equation looks like. So for a flat plate, so dp by dx is 0 here. So if you scale all those things, your x momentum equation looks like u bar del u bar by del x plus v bar del u bar by del y equal to gamma by u infinity del square u bar by del y square. And what have I scaled them with? Where u bar is u by u infinity, free stream velocity, v bar is v by u infinity, same velocity scale is used. Okay, you can go ahead and cross check this, but it should be like that. And scaled energy equation, yeah, I should before that boundary conditions, and at y equal to 0, which represents your flat plate surface, your velocity is 0 due to no slip boundary condition. That translates that your u bar will also be 0. So that is first boundary condition. And at y tending to infinity, or you know, one second. Yeah, y tending to delta also you can take it. your u is u infinity, almost 0.99, but we assume it as 1. So then your u bar becomes 1. So this is your equation number 1. So you should remember this. And scaled energy balance equation looks like u bar del theta by del x plus v bar del theta by del y equal to alpha by u infinity into del square theta by del y square, where see u bar and v bar are same only. Your theta is non-dimensional temperature, which is T by T wall divided by T infinity by T wall. So it is the same scaling. The same scaling was used in class also, and typically this is the scaling that is used. So you can go back and you can, in energy equation we neglect the heat generation term, viscous dissipation term, and then this is nothing but your conduction term, and this is your convection term. And since it's a steady state, we neglect the transient term, which is del theta by del t. So then you should get this thing. And boundary conditions are with boundary conditions at y equal to 0, your temperature is T wall. So that means your theta is 0. And at y tending to delta T, which is thermal boundary layer thickness, which is equal to delta, since Prandtl number is 1. Your T is T infinity. You can say 0.99 times T infinity, but for the sake of ease of calculation, I am taking it as it is at 1. So now, see, okay, 1 second. So see, let's say this is your equation number 2. So now, equations 1 and 2 have similar form, right? With same boundary conditions. And what is the difference? See, boundary conditions are same, only difference are the coefficients. Otherwise, it's a similar governing equation, right? You can see that there are 3 terms and they more or less look like same. Therefore, since they have similar form and boundary conditions are also same, therefore their solutions will also be same. That means your theta and your scale temperature and your scaled velocities, they will give same solution if you solve these 2 equations. And now what you do, you put back, and now your theta is nothing but T by T wall by T infinity by T wall. The scaling that we use, this is u by u infinity. Now you differentiate this equation. So what happens? This 1 by T infinity by T minus this constant terms remains as it is. This will be del T by del y at y equal to 0. And this term will become 1 by u infinity, which is constant, del u by del y at y equal to 0. So simple arithmetic manipulations we are doing. And we know this is nothing but tau wall by mu, because there will be one mu there. And this is nothing but, this is the delta T, and this is nothing but Q wall or flux, boundary flux at wall divided by thermal conductivity. So this all we have done in our last class. we know Cf is defined as tau wall by half rho u infinity square, correct? And then you plug it in the above equation, and what you end up with is, I'm skipping some steps, you can solve them, no, not a big issue. So what you end up with is rho u infinity Cf divided by 2 mu on one side, and that becomes equal to h by k. Now from where did h by k came? See, this q wall is nothing but h into delta t, t wall minus t infinity. So you have to plug that also there. So this thing gets cancelled, this temperature difference, and that minus sign also gets subsumed there, and that's where h by k remains. And on the RHS you can put this and you get this rho u infinity Cf column part. Now you rearrange the terms. On rearranging, you get Cf by 2 equal to HL by k, this is one term, and mu rho u infinity by L, this is the other term. And as we all know, these are nothing but Nusselt number at L and into Reynolds number minus 1. So you can write it as Nusselt number by REL. And since Prandtl number is 1, you can write it like this. And this is your Stanton number at L. So this is what Reynolds analogy is, and the same thing we'll discuss in the class. One thing that you should note here is this Stanton number is defined as Nusselt number by REPR. So, you know, if you simplify again, HL by K into mu by rho infinity L, and this Prandtl number is mu Cp by K, right? So it becomes K by mu Cp. So sometimes this also is asked. So what is the Prandtl number? And they'll just give you this formula. So typically this is the formula that is there. And again, you can multiply by delta T on both the numerator and denominator. So the numerator represents convection heat flux, and the denominator represents axial advection flux. So sometimes, you know, Stanton number is defined as the ratio of convective heat flux in a flow divided by its axial advection flux. Basically, how much axial advection is happening as compared to how much convection at the interface is happening. So that is the definition of this thing, Stanton number. I just thought we can derive it this way also, which is slightly different than what we had in class. Now coming back to the questions. See, before that, it's a very famous question, you know, this relationship between delta and delta T. So what is delta? Delta is you know, hydrodynamic boundary layer, and delta T is thermal boundary layer. So what I mean by that is, so if you have a flat plate like this, and let's say there is a flow at some u infinity velocity and t infinity, and this is at T wall temperature, which is, let's say, higher than T infinity. So there will be two boundary layers here. One will be because of the flow, hydrodynamic boundary layer, and then there will be another boundary layer because of the temperature difference. That will be thermal boundary layer, and at any point this will be your uh, hydrodynamic boundary layer thickness, and at the same point this will be your thermal boundary layer thickness. So how do you know uh, determine which one is greater, which one is smaller? So it's very classic problem, and I'll give you some examples on it. But this is the case where you use uh, you know uh, scaling analysis, and you can get a very good scale. So okay. Hmm. Okay. So now we'll do a small scaling analysis, and you'll realize the scaling. Uh, so now consider energy balance equation. So you have U del T by del X plus V del T by del Y equal to, sorry, alpha will be here. Alpha del square T by del Y square. So this is your simplified energy balance equation within the boundary layer. Now what you do, so now see, the thing is, at the edge of the thermal boundary layer, the velocity is not U infinity, right? Because see, what I mean is U infinity is at this point, but at this point it's not U infinity, right? It's something else. So we assume it as some capital U delta T. So this is the velocity of the fluid at the edge of thermal boundary layer, and this is some delta T by X. X is nothing but L. So this is the scale of your first term. For second term, you have some scale for V directional velocity at the edge of the boundary layer divided by delta T. This is similar to what we did earlier. Here only it is for energy balance equation. And for alpha, it is alpha delta T by thermal boundary layer thickness whole square. So this is first. Now continuity equation. See, we use continuity equation here because here this term is unknown and we need to get rid of it somehow. So that's why we take continuity equation L. So that is del U by del X plus del V by del Y equal to 0, right? So now what is the scale for first? It will be velocity at the edge of the boundary layer, thermal boundary layer, divided by L, and the second scale will come from here. That will be V delta T by delta T. Correct. So that will give you this V delta T scales as U delta T into boundary layer thickness by length. Now what happens? So now you can eliminate, right? So you can put this thing here, and then this also will have same scale. So that is one thing. Importantly, what we do, we assume this unknown uh, velocity at the edge of the thermal boundary layer divided by U infinity is nothing but the ratio, you know, not equal actually, it is a scaling. So we assume they are in same proportion, which is a reasonable approximation. And then what happens? If you do that, you get this unknown term also now you can eliminate, and now you have everything which is in known terms, right? So now put this equation in number 1. So putting 2 in 1. So now you have this u delta t y delta t term, right? This is your first term, this term, and it was scaling to the alpha delta t by delta t square term, which is your this term. So now you put this value here. Then what happens? This becomes u infinity delta t by delta t by L alpha delta t square. Now this delta t gets cancelled. Now you are end up with delta t cube by delta is nothing but alpha L by u infinity, right? And remember, we know this delta scale as delta by L scale as real power minus 1 by 2. This we did some time back only, see, here, see this one. So now if you put those things here, what happens? Hmm. Hmm. So now what you do, you put, we have to introduce this thing in this equation, right? So for that, what you do, uh, we do some manipulation here. This delta will go there, u infinity square will be here, and then 1 L by square will come. So this is just a manipulation, okay? No, nothing big thing I'm doing here. Then this is alpha by u infinity into L square into del. Okay, so this will be L. So now this one, therefore delta t cube by L cube. Now delta by L we know. So this alpha by u infinity L remains as it is, and this becomes REL power minus 1 by 2. Now we further simplify this, and how you do that? You introduce kinematic viscosity term here, and therefore you get this is 1 by RE, this is 1 by Prandtl number, and this is RE power L minus 1 by 2 remains as it is. So in the end, when you simplify and take the cube root of the equation, you get the scaling as REL power minus 1 by 2, Prandtl power minus 1 by 2. Okay, so this is one important thing, and we know delta by L scale as REL minus 1 by 2. This we already know, and we have used this multiple times. So from these two equations, if you divide these two equations, what you get is delta by delta t scale as Prandtl number power 1 by 2. So this is a very famous uh, result, which relates the thermal boundary layer thickness and the hydrodynamic boundary layer thickness. And there were experimental verification for this scaling, and what they observed is this constant is also 1. So you can assume this. and your Prandtl number should be greater than 1. So basically this is valid for water, oil and air also. I mean air it is 0.7 Prandtl number, but we typically consider this scaling valid for air also. Okay. And for liquid metals, you can do similar scaling analysis. I'm not doing it here, otherwise it will take a lot of time. You get liquid metal Prandtl number is less than 1, some 0.1 or something like that. You get the same thing, but the power changes. It becomes half, not 1 by 3. But the important thing to be noted here is since Prandtl number is less than 1, your delta will be less than delta T. And here, since Prandtl number is greater than 1, your delta will be always greater than delta T. So this is also one very famous competitive exam question. Okay. So now we'll take some questions on this topic. And yeah, so regarding that, 1 second. I mean, this is very important result. Okay, try to remember this for any interview or any competitive exam. So yeah, we'll take some questions now. So yeah. So this is a gate question. So it is mentioned that there is a flat plate like this, and you have both hydrodynamic boundary layer and thermal boundary layer on it. U infinity, T infinity is there. There is some wall temperature. So typical flat plate setup. And the question they have given is for a fluid, viscosity is given as 10 to the power minus 3 Pascal second. Cp of the fluid is given as 1 kilojoule per kg Kelvin. K is given as 1 watt per meter Kelvin. And it is mentioned that at certain location along flat plate, the hydrodynamic boundary layer thickness is 5 mm. What will be the thermodynamic boundary layer thickness at same location? So this was the question. It is a like multiple choice question. So I'm not giving the options because it's straightforward. So now you can calculate. First you have to calculate Prandtl number, because then only you can relate the thermal boundary layer and hydrodynamic boundary layer. So Prandtl number is mu Cp by K. Mu is 10 to the power minus 3. Cp is 1 into 10 to the power 3 because it's in kilojoule. And K is 1. So your Prandtl number comes out to be 1. And we know for 1 also you use this 1 by 3 scaling only, okay, typically. So if you do that, delta essentially becomes equal to delta t, which is 5m. So it was same number you have to choose. Basically, both the thicknesses are same. So this was 1 mark question in GET. So if you know this formula, then only you can solve it. If you don't know the correlation, you can't do anything about this question. So that is one thing. What else is there? Uh, 1 second. Hmm. Yeah, so we have not done the correlations yet, right? So I'm not taking those questions. Maybe next class we can do those. Hmm. Yeah, so this was that. Let me just see if I'm missing something. Okay. Yeah, so hmm, hmm. I drink some water, give me some time. Hmm. Okay, so this is a you know uh, subjective question from previous ESE paper. So I mean it's related to the screen friction coefficient or not screen, sorry, drag coefficient. So that is why I'm taking it. It's basically the derivation of it for exact things. So for a flow over a flat plate for okay anyway the velocity profile is given as u by infinity is nothing but 3 by 2 y by delta minus 1 by 2 y by delta cube. That is given in question. And hydrodynamic boundary layer thickness delta is given as square root 280 u by 13 into u infinity. So it is given in the question itself. Then develop expression for local drag coefficient CF is what is asked. Okay. So See, it's a play on the definition of local drag coefficient CF. So we know that CF is nothing but tau wall by half rho u infinity square, right? This is the definition of CF. Now we know tau wall is nothing but del u by del y at y equal to 0, which is your wall coordinate, divided by half rho u infinity square. So here they have given you velocity profile, they have given you what you say, this delta profile as well, and you have to just plug in those things. So now if you take the gradient of your velocity profile, what you get, this will give you 3 by 2 into 1 by delta minus 1 by 2 into this will be 3 into y by delta square into 1 by delta cube, right? Am I correct? Yeah. And therefore, if you put y equal to 0 and this, you get 3 by 2 delta, because the second term goes to 0. This term goes to 0 at y equal to delta, y equal to 0. So now they have given you delta expression also, right? So uh, you can use that here, or maybe at the last location we'll put it. Maybe that will simplify our problem. So now you have CF, which will be del mu into this 3 by 2 delta divided by half rho u infinity square. So this 2 gets cancelled. So here it remains 3 mu divided by rho u infinity square into delta. Correct, no? 1 second. Yeah, I think there is some problem here, because u by u infinity is dimensionless, right? So there should be delta by x here. Yeah, so then only it makes sense. Okay, so now what you do? You multiply and divide with so this 3 remains as it is. And you do this rho u infinity. 1 second. Yeah, there will be this 1 by u infinity, right? Because this is u by u infinity. So you'll have 3 u infinity here, u infinity here, and then only 1 will be there. Yeah. So then only your x will come into picture, right? And now this becomes x by delta. So basically your CF is 3 remains as it is because it's a coefficient. And this is your RE power x minus 1. And this del by x, uh, you know, one second, I think there is something 3 by 2 u infinity into 1 by delta. So you multiply them. Mm, yeah, so now this is rho u infinity by mu, that is your Rex. Del by x, this is ulta of that. So this becomes 13 by 280 into u infinity by u. Now the question is, do we need to solve further? Because as far as I can see, it is solved only. See, one thing you can do is, again, you put this u by u delta, then this whole thing becomes function of delta. But do we want that? One second. One second, let me check this question. I think there is some problem in the question. So, I think into Rex is supposed to be there. Delta is 5x by Rex. So delta by x will be 5 by Rex. Yeah, I think this expression here is wrong, because see, if that is the expression, it remains like this, but this is not what I wanted, so I'll change. I think this is what is the problem here. So this is nothing but given as 5 by root Rex, so Reynolds number at x. So this is for the delta expression. So if you do that, what you end up with is 3 into Rex power minus 1, and x by delta is root Rex divided by 5. Correct? Ulta. So therefore your CF becomes 0.6 times Rex power minus 1 by 2, which implies your CF is nothing but 0.6 divided by Rex power 1 by 2, which is, if you want to write it again, something like this. So this is the final form. So, and this is pretty much close to exact thing. 0.664 is what you exactly take. We will discuss those things later. So yeah, that is one thing. Then what else is there? Yeah, so now this is also done. I had some questions from previous years. That's what I'm trying to check here. Yeah, we are skipping one important topic here, which is the dimensionless coefficients. So I find this, because what happens when you learn so many numbers, dimensionless numbers in this course, it is common thing that people forget what is what and what are we even studying. So not to do that, uh, you know, I'll just list down a table which helps, in our remembering those things. So yeah, so let's say, what should we say? See, there are two numbers, right? This Prandtl number, Schmidt number. So they, and Lewis number, I think, yeah. Lewis number is the third in their category. Let me just confirm once. Yeah. So, and then there is Nusselt number, which is heat transfer thing. Reynolds number, Sherwood number, Schmidt number is also there. Prandtl, Schmidt, and Lewis, and Nusselt and Sherwood, and Reynolds. So, basically, they are dimensionless heat fluxes. Oh, sorry, dimensionless temperature gradient. Okay. So what I mean by this is, you should remember this in easy form, and let me just see if I can help you with that, because otherwise it becomes very confusing. So, see, this Prandtl, Schmidt, and Lewis, they are dependent, or they are diffusivity ratios. So they come into one category. Then this Nusselt and Sherwood number, so they represent dimensionless temperature gradient, dimensionless concentration gradient, and this wall shear stress maybe you can consider, which is mu del u by del y. And if you non-dimensionalize it, you just want to know, yeah, I think CF you can consider, because it is a scaled version of those. So those three come together, and then this Reynolds number is, this inertia by those. So basically, to remember this, yeah. So I'm just seeing if any concise presentation is there or not. So that way it will be easy. Just give me a second. Yeah, I think we have to go this way only. So you can remember it this way: this Prandtl, Schmidt, and Lewis. So these guys come together, and they are ratios of diffusivities. What I mean by that is, Prandtl, as we all know, it's mu Cp by K, and if you do some manipulation, you'll get kinematic viscosity upon thermal diffusivity. And Schmidt is nothing but it correlates mass transfer with your momentum transfer. So that will be your gamma by mass diffusion coefficient. So this is your thermal, or should I say momentum plus thermal. and Schmidt number represents momentum plus concentration. So when there is a concentration boundary layer, Schmidt number will decide uh, the thickness of what is what. So basically what I mean is, in that case, this del by del C will be scaled as some Schmidt number power n. That n will be typically 1 by 3, but let's not jump there, but you should remember this way. So this is A, B and C. And C, Lewis number, now we can correlate them. So basically Lewis number will it will correlate the other two guys, so that will be alpha by D. So sometimes people call this as Schmidt number by Prandtl number also, but let's leave it at that. So here you can say thermal plus concentration. But see, Lewis number is not that well discussed, because you cannot have only thermal and only concentration boundary layer, right? You will have to have momentum, then only you will have advection effects, and then only boundary layers will develop over the length. Therefore, uh, typically Prandtl and Schmidt number will be more used, and as a derivative of that, Lewis number comes into picture. And similar to what Schmidt number represents, this will also represent what will it represent? Del by del T. So this will also represent delta T by delta C and some power n, Lewis number some power n. So this is one thing that you should remember, because many a times in competitive exams they'll just ask you what does Lewis number represents, what does Schmidt number represents. So that is that. See, if you remember, Prandtl number you will remember. You should remember Schmidt number, and then S by P is L. So that will also you can remember. And now the second note is this guys, Nusselt number, Sherwood number, and this drag coefficient. So all these come together, and what they represent is non-dimensionalized gradients at the wall. Okay, which is y equal to 0. So basically, the Nusselt number, as we saw in class, is nothing but del T star by del Y star at Y star equal to 0, right? This was done in class. So this represents your see, it comes out to be HL by K, right? So you can further modify it as L by KA divided by 1 by HA. So just to have that analogy of resistances we used right initially for conduction. So here you can see conduction resistance in fluid, which represents the numerator divided by resistance to convective heat transfer. So that is what Nusselt number represents. Similar fashion, your Sherwood number is nothing but non-dimensionalized concentration gradient. So something like this. I'm not giving you the scalings because that was already discussed in the class. It becomes mass transfer coefficient into length divided by the diffusion coefficient. So again, you can define it similar fashion. numerator will change. It's not conduction resistance now, it is resistance to mass diffusion. So I should say here also conduction resistance to thermal diffusion, and then similar definition you can use for but here it won't be thermal diffusion, it will be mass diffusion. Correct. And yeah, the CF, nothing but it represents tau wall by rho u infinity square half. So it is also, in a sense, it's also scaled velocity gradient. So I mean, you can have this CF formula, etc. But the point that I'm trying to make is this three guys will come together. Okay, and if you remember this way, maybe the confusion will not be there, because many a times people get confused with the numbers, and then they mix up Sherwood everything together, and it all becomes jumbo in their head. So to avoid that, you can classify them and study like this, and then extension to the CF, you have this Reynolds analogy, etc. Right? So that also you can just mention here. This CF by 2, and remember this 2 also, because the people forget to PR power, and this they call it as if it's a heat transfer, they represent standard number for heat transfer with subscript H, and they call this as Colburn factor. These guys, this is Colburn factor. Not widely used term, but you should know, because in some question, if they just mention this is the Colburn factor, you should know. And this is valid for some range, which is actually very broad range. And again, the other analogy is this for mass transfer. They represent it as it will be Schmidt here, not Prandtl. And they use this M as the coefficient for that. So this was given in class only. I'm just giving here for your benefit. Remember this. And one more thing is, these are valid for laminar plus turbulent flows. So you should remember that, because see what happens if it is laminar flow, you will have certain correlation for Nusselt number. If it is a turbulent flow, you will have different correlation for Nusselt number. So Nusselt number will change, but this analogy will be still valid, because it doesn't, the derivation you have seen, it doesn't depend on laminar or turbulent. Like that. So yeah, I think we'll take some questions now, because I think I've covered most of the theory part. So for that, let me just see. See, without correlations, taking questions from this area is thoda difficult. But nonetheless, we have some previous year questions, and we'll do that. So question is like this. It's a flat plate case only. For a flat plate case, U infinity is given as 1 meter per second. Length of the plate in the direction of the flow is 1 meter. Average mass transfer coefficient is given as 10 to the power minus 2 meter per second. Then we need to calculate following parameters, which are nothing but Sherwood number, average Sherwood number for whole plate, Reynolds number for the plate, Schmidt number, and Colburn factor for mass transfer. The fluid is, I mean, see, it's like this. I'll draw some figure, then only it will make sense. So the thing is like this. It's a flat plate. There is a small or thin layer of fluid, which is shown by darker black colors here. Naphthalene. So the fluid is naphthalene. Okay, so air is flowing at U infinity, and there is this naphthalene fluid which is getting evaporated, and that is what getting creating a concentration boundary layer, something like this. So they have given the mass diffusion coefficient as 0.62 into 10 to the power minus 5 meter per second, and see maybe okay. The point I was trying to make is units of gamma, d, and alpha are all meter square per second. So this is also very important hint. Sometimes that helps. So this will be meter square per second. And your kinematic viscosity is 15.89 into 10 to the power minus 6 meter square per second. So this is what all the information is given. So now we have to solve this. So now question already given. Solution. So first is Reynolds number. So that is easy, right? Reynolds number is U infinity into L by kinematic viscosity. So that will be 1 into 1 divided by 15.89 into 10 to the power minus 6. You'll get 6.29 into 10 to the power 4. So it's less than 10 to the power 5, so flow is still laminar. Then what else is there? Schmidt number is function of fluid properties, and just now we saw it is this kinematic viscosity divided by mass diffusion coefficient. So this we have 15.89 into 10 to the power minus 6, and this is 0.62 into 10 to the power minus 5. So this will be basically 1.58 divided by 0.6. So almost double. Yeah. So if you do exact calculation, it will be 2.56. Now we have to calculate Sherwood number also, right? So Sherwood number, average Sherwood number will be average mass transfer coefficient length divided by mass transfer, right? So D will be here. So 10 to the power minus 2 into 1 divided by 0.62 into 10 to the power minus 5. If you solve this, you should get 1613. Now this Coleman factor for mass transfer, it will be nothing but Stanton number for mass transfer into Schmidt number raised to 2 by 3, right? We saw that. Now, what is the Stanton number for mass transfer? Will be nothing but Sherwood number by Reynolds number and Schmidt number, right? Correct, no? Yeah, I think it's correct because everything gets the analogy remains same only. So where is Stanton number? Yeah, so it is nothing but Sherwood number. Since we are talking about averages, I think this will also be called, should be called as average Stanton number divided by Reynolds number into Schmidt number, and then you have Schmidt number power 2 by 3. So you know, this guys will get, it will be Sherwood number divided by Reynolds number into Schmidt power 1 by 3. And if you solve this, you should get the Coleman factor as, because we already calculated Schmidt number, Reynolds number, Schmidt number, so everything we have already done. So you put those values and you can cross check the answer. You should get something like this, 0.0187. This was just an exercise, to get familiar with the definitions. So now, let me see if any other question is there. So in this case, Ts minus T infinity. Okay. But the question is, one second, let me just think about this, if it is correct or wrong. Yeah, so there is this question in which there is a sphere which is kept in a dry air environment, but water calculate the mass transfer coefficient. There is some issue with this question. Let me just think about it 1 second. CP alpha. OS rho infinity. Weighted plate determinant. Okay, so we'll take this question with. So what it says is similar to this case. There is some wetted water. So instead of naphthalene, now we have water for a flat plate with thin water layer at the top. So basically, instead of naphthalene, there is a water and there is a dry air. So same case, only naphthalene is replaced with water. And then, this plate, they have given some information about the plate. So, okay, I'll draw the figure again only so that I can mention the things in the figure itself. So that will be better. So here it is water. Okay. So this dry air is at 32 degrees Celsius. The plate area is 0.2 meter square. Average heat transfer coefficient is 20 watt per meter square because the plate temperature is T wall or T plate is 27 degrees. So there is air which is at 32 degrees, plate is at 27, so there will be heat transfer, right? Because of the 5 degrees Celsius delta T. And due to that heat transfer, we end up with the average heat transfer coefficient of 20 watt per meter square. And it is given that, for this water, HFG is given as, which is, heat of evaporation 4.38 into 10 to the power 6 joule per kg, and density saturation is given as 0.002556 kg per meter cube, because this water is saturated and it's getting evaporated, so its enthalpy of evaporation and saturation density is given. So, and now the question is, it is a two-part question. Determine the average mass transfer coefficient if power required to maintain the plate at constant temperature of 27 degrees Celsius is 432 watts. It's not a question, it's a normal sentence. So what it means is basically when the water gets evaporated, the plate will become cold because it takes, it needs energy, which is the enthalpy of evaporation. So it will take that energy from plate, and plate, uh, if there is no heater or no power supplied to the plate, the internal energy of the plate will be used for this evaporation, and that will result in the temperature drop of the plate. So in this example, we want the plate to be at constant 27 degrees Celsius temperature. We don't want it to be cooled anymore. So if that is the case, you need to supply at least 432 watts of power. And if that is the case, what is the average mass transfer coefficient is asked. Okay, so this is nothing but our in our symbols, mass transfer coefficient average. So now see, you can by energy balance, you know, what is the 1 second. Yeah, so if you consider this as your control volume, the plate only, so if you consider this as your control volume, and if I draw it somewhere here, so let's say this is your plate, right? So heater is providing power, so heater power, let's say we call it as pH, and there is heat transfer from plate or ambient to the plate, right? So because ambient is at 32 and plate is at 27, so 32 degrees Celsius T infinity to T wall of 27 degrees. So there is heat transfer, power coming from heat transfer. So maybe I'll put it as delta T, power or energy interaction due to this thing, what you call uh, delta T, and then there is energy going out in terms of mass, because there is a dry air outside, so this air is dry, so there is no water vapor in it, so water is going from plate to uh, ambient dry air, so that will be energy interaction due to concentration difference. I am putting P as the symbol, but that represents energy per unit time. So by energy balance, if you see, what will you see? So heater power plus delta T power will be equal to delta C, right? So correct, no? So heater power. So we are interested in this only, right? Because we need mass transfer coefficient. So yeah. So now heater power they have given as 432 watts. Okay, I'll put it as symbol only. We'll put numbers in the next step. So heater power remains as it is. Now what is your delta T power? That will be H surface of the plate into T infinity minus T wall. And what will be your, so this will be average H, this will be your average mass transfer coefficient, and I'll write it here. This will be your average mass transfer coefficient into the density difference between uh, plate minus density difference of infinity, density at the water vapor density at the outside the concentration boundary layer into HFG. So since HFG is given in per kg, so we don't have to do anything here. And Now see, the heater power is 432, that is given. Average heat transfer coefficient is 20, that is also given. And area of the plate is 0.2. Delta T is 5. This is unknown. Density is also given, right? Uh, 0. One second, it is 0.02. Hmm. 1 divided by 1000. 0.00. Okay. So this saturated density 0.002556 minus 0. Because see this rho infinity, it will be 0 because the air is dry, right? So concentration gradient will be calculated like that. So this is 0. And HFG is also given, which is where is it? Yeah, 2.414 into 10 to the power 6. So one equation, one unknown, and yeah, there will be one area term here also, because then units won't match. Yeah, because this kg per meter cube, joule per kg, so this becomes joule per meter cube. Correct, no? Joule per second we want. Yeah. So into this area of 0.2. So if you solve this, you should get the final answer as 0.0363 meter per second. I am leaving the calculation for you to verify, but this is the correct answer. Now, second part of the question is in this question, what they did, they changed the uh, plate temperature. So now here, what will be the heater power requirement if plate temperature is increased to 37 degrees, and assume T infinity, H bar and H bar M remain constant. So basically whatever we calculated in the first part of the question, uh, the same coefficients, and air is still at 32 degrees, dry air. We have to see that. So now and here they have given that at 37 degrees saturation density, saturated water density is 0.04. 361. 1 second. Yeah, I think there is only 0.0. In the data there is some mistake, I think. Yeah, something like this. This is kg per meter cube, and HFG is more or less same only, it doesn't change much in 10 degrees. Oh, 1 second. Earlier it was 438. Oh, okay, sorry, my bad. So this was 438 earlier. Yeah, now it is 414. So slight change is there. because the temperature is more now. So the liquid or the saturated water that is getting evaporated, it is getting evaporated at 10 degrees higher than the earlier case. Therefore, density and HFG changes. So now, same energy balance will be same, but in this case, there will be heat transfer from the plate to the ambient, right? So what will happen in this case is, if I can copy this again. So in this case, this is degree Celsius. Sorry. So this is degree Celsius, but this becomes 37 now, and the direction of heat transfer changes. So it is from plate to plate to ambient now. So now, if you write the energy balance, what you'll get, whatever is coming to the plate is heater power, and what is going out is delta T plus power loss or power out due to concentration gradient. So same thing. Now we have to take H bar A into delta T plus, here it will be H bar M into A into HFG into rho saturation minus rho infinity. So same thing. So since they have mentioned that H bar remains same and HM bar remains same, you don't have to change those. Now H bar is 20, area is 0.2, delta T is 5 plus H bar is 0.0363, area is 0.2, HFG is 2.414 into 10 to the power 6, and the saturation density they have mentioned 0.04361 minus 0, because it's a dry air, so therefore 0. So now if you simplify, you'll get heater power as 784 watts. So I am neglecting the one order, but you should get around 784. So this is how you have to do. So we are already at 743. Check if I have missed something. Yeah, so I think more or less we covered, because see, we can limited time and limit, like we cannot use those correlations, right? If we can, then there are many questions. So anyway, yeah, so I think today we can stop here, because uh, see, mostly the correlation stuff will happen next week, and what I mean by that is, let me just see. So yeah, so correlation, because we can take more examples next week, because we'll have directly Nusselt number correlations there. So right now we'll stop. If you have any doubts or anything, you can post, or let me just see the assignment, weekly assignment, if anything is there. Yeah, so we have discussed the coefficients, boundary layer also we discussed. Yeah, it's just a Prandtl number thing. Then yeah, so basically what happens, so there is a question on drag and like that, so I'll just quickly, I'll not take any numbers, but let's say if there is a plate like this, and what is there is parallel to the airstream, okay, u infinity is given as, or some u infinity is there, and some t infinity is there, and as usual you'll have wall temperature for plate. Yeah, in this problem there is a flow from both sides of the plate, and drag force comes out to be 0.075 Newton. This is the total drag force, and what is asked is what is the rate of heat transfer from both the sides. So what I mean, I am not going to solve this because it's your assignment question, but the idea is see, if there is any question involving drag force, first thing that should come to your mind is you can calculate wall shear stress based on the drag force. Now, wall shear stress will be force upon area. So now, since the drag is on the both sides, you have to take area which will be summation of top side area and the bottom side area. Then you'll get drag wall shear stress, right? Now we also note that wall shear stress is Cf by half rho U infinity square, right? So density is given in the problem usually. U infinity is also given, and from here you get Cf. Some value of Cf you'll get, and Cf is I think non-dimensionalized, so no units here. And then you have to use this Reynolds-Coleman analogy, and what that means is this standard. So basically you'll have Cf is Stanton number into Prandtl number power 2 by 3, right? So Prandtl number you can calculate. It is sometimes it is directly given, otherwise mu Cp by k you have to do. And this Stanton number is nothing but Nusselt number divided by REPR. So you can simplify here itself. It will become Nusselt number by RE into PR power minus 1 by 3. So from here you get the see Reynolds number you have because rho U infinity by gamma is known typically. So you'll get Reynolds number, Nusselt number from here, and Nusselt number is HL by K, right? So we are talking about all average parameters here. So this will give you average heat transfer coefficient for the whole length of the plate, and then your heat transfer rate will be H bar into area into Ts minus T infinity or T infinity minus Ts depending on which is higher, and remain and consider this total area of the plate because heat transfer is taking from both the sides. So if you do that, you should get the answer. So this is a straightforward question based on the this Reynolds-Coleman analogy. So you should be able to do that. Yeah, similar question next also. There also they are asking power. That is also this heat transfer rate only in steady state. Yeah, I think then you should be able to solve the assignment 5 questions also. And so we'll stop for today here, and I'll see you next class. Okay. Thank you for your time, and see you.